I want to show you that from quantum field theory, you can derive the Schrödinger equation, or if you want, quantum mechanics. So quantum mechanics is contained in quantum field theory, and there is a way to derive it. And I want to start from a Lagrangian density. Let me just call it Lagrangian. And in particular, we will consider the Lagrangian of a complex scalar field. D mu psi star, so this is the complex conjugate, d mu psi minus m squared psi star psi. So if you want, this is just mod psi squared. I'm going to write it like this. I'm considering units such that h bar is equal to 1 and the speed of light is also equal to 1. So with this kind of units, you can see that the velocities are dimensionless, which means that length is equal to time in terms of units. And h bar equal to 1 means that energy times time, so h bar as the units of energy times time, and therefore it means that energy is time to the minus 1, or if you want, also length to the minus 1, according to this. So we can keep that in mind, but it's not important for this video. Now, from this Lagrangian, we can write the equations of motion. In general, we have to treat psi star and psi as two independent fields. So we have two independent field equations, if you want, that we can write down. So we can write dl d psi star minus d mu dl d mu psi star equal to 0. This is one where we put psi star here, and in principle we also have another one where instead of psi star we consider psi. Now I'm just going to write this. As I said, you have to consider psi and psi star to be independent before, in the Lagrangian, so before deriving the equations of motion. And finally, we get m squared psi plus d mu psi equal to 0. Now here we have the equation of motion, and without, let's say, calculating the other equation of motion, where we put psi instead of psi star, it's easy to derive the other equation of motion simply by taking the star of this equation. So we would have something like this. We just put the star. Simple as that. But I'm going to consider this one. And what I'm going to do now is I'm going to make a substitution. So I have psi equal to, so we define it to be e to the minus I mt psi tilde, and in general we can multiply this by a constant. And by the way, please do not confuse this constant with the speed of light. And this constant m here is just the mass of the particle. So we have m, and if we consider the units, instead of imt we would have imc squared t divided by h bar. So this is how we can make this dimensionless. Of course, this minus sign would stay here, but just to, let's say, let you understand it more thoroughly. If we add the units, we would have something like this, because mc squared is energy. Energy times time is h bar, if you want. It's the same units of h bar. And then we divide by h bar. So h bar is an action, right? Because we are integrating something which has the dimension of energy dt in the action. So action is energy. So this is energy. Lagrangian in general in classical physics, you think about it as units of energy, because in classical mechanics, for example, here you have the kinetic energy minus the potential energy dt. So h as really the units of an action. Anyway, this is not important. I'm not going to consider this a constant c. And by the way, do not confuse this c, as I said, with this constant. They are different. And let me go back. We simply have to make this substitution and put it there in that equation. So when you put it in that equation, we have m squared e to the minus I mt psi tilde. Then we have the constant, but everything is equal. I mean, the left-hand side is equal to 0. So the constant can be simplified, right? And then we have plus dt squared minus del squared. And this comes from del mu. I mean, this del mu would be era mu nu del mu. And I'm considering a signature of the kind 1 minus 1 minus 1 minus 1. And therefore you can write it like this. And this should be applied to e to the minus imt psi tilde equal to 0, like this. So we can write this as m squared e to the minus imt psi tilde plus, then I have dt again. So one dt is going to act on this. So I'm going to rewrite it as minus im e to the minus imt psi tilde plus e to the minus imt dt psi tilde, and then I have minus e to the minus imt del squared psi equal to 0. Now, of course, psi tilde and psi, they are both functions of x and t, right? But e to the minus imt is a function of time only. So this Laplacian operator is going to act on psi tilde, whereas dt is going to act on both of them. So the derivative with respect to time of that expression is a little bit more complicated. And now I can calculate this time derivative. We have m squared e to the minus imt psi tilde, and then I have plus minus m squared e to the minus imt psi tilde. Then here I have minus 2im e to the minus imt dt psi tilde plus e to the minus imt dt squared psi tilde, and then I have minus e to the minus imt del squared psi tilde, and this is equal to 0. Now you can see that this term will simplify with this, and finally we are left with a minus 2im dt psi tilde plus dt squared psi tilde minus del squared psi tilde equal to 0. Now, in the non-relativistic limit, so we want to go back to quantum mechanics. So in quantum mechanics in general, the velocities are much smaller than the speed of light because we do not have covariant equations. And also, if you think about it, the Schrödinger equation actually comes from a discretization of the classical energy. So what we need to do here is to consider the fact that dt squared psi tilde mode of this is much smaller than m times the mode of dt psi tilde, if you think about it, because a second derivative with respect to time of psi is going to give us something which is proportional to the classical energy squared, and the classical energy squared is proportional to momentum squared. So this is the momentum squared of the particle, whereas of course this one here will be proportional, will be of the order of momentum p. So this means that p should be much smaller than m. And if we put our units back, here we would have mc, right? And momentum would be m times v, the velocity of the particle. So of course the velocity v is much smaller than the speed of light, right? So that's why we can make this assumption, and therefore this term would be neglected. So this is negligible. And lo and behold, what you find from here is I dt psi tilde equal to minus del squared divided by 2m psi tilde. And what is this? Well, this is the Schrödinger equation. Now, at this point, you might think, well, now we are done, right? We have found the Schrödinger equation, so quantum field theory, in this case, will lead us to the Schrödinger equation. But actually, it's not so easy. It's more complicated than that. Why? Well, you have to think that the difference in this case is that psi, or psi tilde, is not a probability amplitude, just like in quantum mechanics. But psi tilde is a field. So conceptually, there is quite a huge difference between a field and a probability amplitude. So we cannot really say that we have derived the actual Schrödinger equation that we have in quantum mechanics. We have to do more than that. So how do we go back to quantum mechanics? It's not too complicated, but there are some calculations to be done, and I would like to go through the procedure with you. So try to follow me. First, I'm going to define an operator, a vector operator, so I'm going to put this arrow here to denote the fact that this is actually a vector, and I'm going to define it like this, integral d3p, so we are integrating in momentum space, divided by 2 pi cubed, and then here we have the 3 momentum, p, and then I have ap dagger ap. Now, these AP and AP dagger, in this case, they are operators. So when I'm considering, let's say, a classical theory, instead of the dagger, I would simply have the star to denote the fact that this is a complex conjugate operation. But this is the dagger, so in this case, I have to treat these as operators. And how do I define AP and AP dagger? Well, if we consider the function psi tilde of x, and in particular, in this case, I'm just going to consider a function of x, not a function of time. And am I allowed to do so? Am I allowed to drop the time dependence? Well, yes. Let me say this in a moment, but first let me write down the equation. So I have integration d3p divided by 2 pi cubed ap e to the I p dot x dot product in this case. So psi tilde dagger, when in this case I'm considering operators because I'm turning these objects into operators. So here I would have the dagger, and here I would have a minus. So AP appears in the expansion of these fields that I'm just quantizing, okay? And so the question that I would like to ask is, well, are we allowed to treat psi tilde as just a function of x instead of a function of x and t? Because in general, psi tilde and also psi would be a function of x and also of t. We are allowed to do so if we consider, for example, this equation here, and we define psi tilde of tx as e to the minus I h t psi tilde of x. In this case, if you plug this into the equation, you would have h psi tilde of x equal to minus del squared divided by 2m psi tilde of x, like this. And in the case of the Schrödinger equation, we can do that. So we can rewrite psi of tx as an operator. If we treat this as an operator, here we have a unitary operator acting on a function of space. So in particular, this operator here gives us the time evolution from, for example, t equal to 0 to some time t. So this is something that in quantum mechanics we can do, and therefore we can just consider a function of x, of space, and then we can go back to time by considering this unitary operator, and we can find our time dependence as well. But in this case, we are allowed to consider only the part of the function that depends on space. And that's what I'm going to do. So at this point, I want to show you that this is actually a momentum operator. And how do we find that? Well, we act with this operator P on a one particle state. And how do I define a one particle state? Well, I can define it as this creation operator, AQ dagger. So in this case, I'm not going to derive the fact that this is a creation operator. So if we act on the vacuum that I'm going to denote like this, with this operator, we're going to get one particle with momentum that in this case I can call Q. And I want to show you that the momentum of this state is indeed Q. How do I show that? Well, I have to show that this operator, P, acting on AQ dagger vacuum, this should be equal to Q, AQ dagger vacuum. But I want to show this. I want to prove that this is the case. So if this is the case, then we can treat P, this P here, as the momentum operator. How can we do that? Well, we have to work out the details. So we start from here. So we have P acting on AQ dagger vacuum. This is equal to integral d3p divided by 2 pi cubed p AP dagger. And then I have AP AQ dagger 0. And I can rewrite that like this. AP AQ dagger minus AQ dagger AP plus AQ dagger AP acting on the vacuum. So I have simply added and subtracted the same term. This minus this, of course, they cancel and we get back the original expression. But now the advantage is that here I have a commutator between AP and AQ dagger. We can show, and we will do it later. I want to show this to you, even if for those people that have already followed a course on quantum field theory, this will be quite easy to understand. But I want to show it later for the sake of convenience. This is equal to 2 pi cubed. And then here we have the three-dimensional Dirac delta, delta 3 of P minus Q. I will show it later, as I said, but for now, let's take this for granted. And by the way, now that we have also this term, when this term acts on the vacuum, you can see that AP acting on the vacuum will annihilate the vacuum, so we'll get 0. Therefore, this term will give us no contribution. And in this case, as I said, I don't want to get into the fact that this is an annihilation operator and this is a creation operator. So this is something that I will take for granted. But it's not complicated to understand why they are creation operators and annihilation operators. You can also try to understand it from also the calculations that we will do later, and you can try to work it out yourself if you are not convinced that they should be treated as creation operators and annihilation operators. Anyway, so here we can make the substitution. We can plug this into the equation, and we get integral d3p p AP dagger delta 3 of P minus Q acting on the vacuum. So this AP dagger will act on the vacuum, so it will create a particle. We have this three-dimensional Dirac delta, so it's easy to integrate this, because when we integrate this three-dimensional delta, d3p, we will get 1. And instead of p, here we will have to rewrite q, because we have this delta. So we can evaluate this p at p equal to q, because of the presence of this argument here in the delta. An AP dagger will be AQ dagger. So basically what we find is Q, AQ dagger, 0. This is what we wanted to find. So indeed, this operator P is momentum.